we have discussed some important aspects related to coordination compounds in our previous lectures. Today, in continuation, we are going to discuss coordination sphere, ionization sphere, coordination number and stereochemistry for various coordination numbers. Before proceeding further, let us recall what we have discussed earlier. In previous lecture, we discussed classification of ligands on the basis of number of donor sites, chelate complexes, the chelate effect and the thermodynamic stability of chelate complexes. Before defining coordination sphere, let us discuss what is a coordination compound. A complex or coordination compound is a compound consisting either of complex ions and other ions of opposite charge or of a neutral complex species. For example, the compound K4FeCN6 of the complex contains 1 FeCN6 4 plus and 4 K plus ions. Now we will define coordination sphere. Ligand with central metal ion is kept in square bracket, retains its identity in the same form and is called coordination sphere. This coordination sphere is non-ionizable. You can see here the metal ion cobalt and 6 ligands NH3 are kept in square brackets and this identity is known as coordination sphere. Now we will define ionization sphere. The part present outside of the square bracket is called ionization sphere. Ionization sphere is ionizable. To completely understand a coordination compound, we must also know what is coordination number. Coordination number can be defined as the number of monodentate ligands attached to central atom or ion. The coordination number of a metal atom in a complex is the total number of bonds the metal atom forms with ligands. In FeH2O6 2 plus, the iron atom bonds to each oxygen atom in the 6 water molecules. Therefore, the coordination number of iron in this ion is 6. In 1893, at the age of 26, Alfred Werner produced his classic coordination theory. The main points of this theory are that metals possess two types of valencies, the primary or ionizable valency and the secondary valency. The primary or ionizable valency, which must be satisfied by negative ions and is what is now referred to as the oxidation state, and the secondary valency, which has fixed directions with respect to the central metal and can be satisfied by either negative ions or neutral molecules. This is the basis for the various stereochemistries found amongst coordination compounds. The term secondary valency has been superseded by the term coordination number. This may be defined as the number of donor atoms associated with the central metal atom or ion. The most commonly occurring coordination numbers for transition elements are 4 and 6, but all values from 2 to 9 are known and a few examples of even higher ones have been established. Now we will discuss the most important factors determining the most favorable coordination number for a particular metal and ligand. If electrostatic forces are dominant, the attractions between the metal and the ligands should exceed the destabilizing repulsions between the ligands. The attractions are proportional to the product of the charges on the metal and the ligand, whereas the repulsions are proportional to the square of the ligand charge. High cation charge and low ligand charge should consequently favor high coordination numbers. There must be an upper limit to the number of molecules or atoms of a particular ligand which can be physically fitted around a particular cation. For monoatomic ligands, this limit will be dependent on the radius ratio of cation and ligand. Where covalency is important, the distribution of charge is equalized by the transference of charge in the form of lone pairs of electrons from the ligands to cations. The more polarizable the ligand, the lower the coordination number required to satisfy the particular cation. The availability of empty metal orbitals of suitable symmetries and energies to accommodate electron pairs from the ligands must also be important in covalent compounds. This is probably one of the main reasons why the lowest coordination number, that is 2 and 3, are to be found in silver, gold or mercury region of the periodic table, where the d subshell has been filled. D subshell means D subshell has 10 electrons. However, it would be unwise to draw the converse conclusion that the highest coordinations are found amongst the early members of the transition and inner transition series because of the availability of empty d or f orbitals. It seems more likely that these high coordination numbers are achieved by electrostatic attractions between highly charged but rather large cations and a large number of relatively non-polarizable ligands. We will now discuss the representative examples of the stereochemistries associated with each of the various coordination numbers. First, we are taking coordination number 2. There is only a limited number of complex ions with a coordination number of 2, and these are typically found among +1 ions of copper, silver and gold and +2 of mercury. These are all D10 complexes, that is, these all have 10 electrons in the d subshell of outermost shell. The geometrical arrangement of these complexes tends to be linear. In general, these bis complexes readily accept additional ligands to give complexes with higher coordination. Examples for coordination number 2 are HgCN2, CuCl2-, AgNH3 2+. For coordination number 2, structure is linear and hybridization is sp. In linear structure, the two metal ligand bonds have an angle of 180 degree. Here you can see a linear structure with a complex AgNH3 2+. Here is silver metal ion attached to two ammonia ligands. These are two coordinate bonds and the structure is linear with ligand metal ligand bond angle equal to 180 degree. Now we are proceeding to coordination number 3. 3 coordination in metal complexes is also very unusual or rare. Structure for coordination number 3 is triangular planar with sp2 hybridization. Some examples are Hg(I3-), Pt p(PH3) whole thrice. Here p(PH3) is the ligand named triphenyl phosphine. You can see ligand metal ligand bond angle in this structure is equal to 120 degrees. For coordination number 4, there are two common typical geometries. These are tetrahedral or square planar. Two different coordination polyhedra are associated with a coordination number of 4, that is tetrahedral and square planar structure. The tendency towards the formation of a tetrahedral structure can be rationalized in terms of steric constraints, that is, as ligands increase in charge or size, there is a need for the ligands to be as far away from each other as possible. Here you can see a tetrahedral structure of CD NH3 2 plus. Cadmium 2 plus is the metal ion and 4 ammonia ligands are attached to cadmium 2 plus in tetrahedral structure. In tetrahedral structure, ligand metal ligand bond angle is 109 degrees 28 minutes. Due to steric constraints, square planar structures are not favored by relatively large ligands. Relatively small ligands do not favor square planar structures either. The ligands may be so small that two additional ligands may be readily accommodated below and above the square planar, giving an octahedral complex. Here is an example of a complex with square planar geometry. Cisplatin is a complex with square planar geometry. In square planar geometry, d-sp2 hybridization is involved and the ligand metal ligand bond angle is 90 degrees. Here is another example of a complex with square planar geometry, CuH2O4 2 plus. Here Cu2 plus metal ion is coordinated to 4 H2O ligands and the complex has a square planar geometry. Now the coordination number 5 is less common than complexes with coordination number 4 or 6. Typical geometries for coordination number 5 are trigonal bipyramidal and square pyramidal. There is an example with trigonal bipyramidal geometry. You can see in trigonal bipyramidal geometry there are two types of bonds. 3 bonds are equatorial and 2 bonds are axial. One bond angle between ligand, metal and ligand is 120 degrees and one bond angle between ligand, metal, ligand is 90 degrees. So, two types of bond angles are found in trigonal bipyramidal geometry. Now, there is an example with the square pyramidal geometry. In square pyramidal geometry, you can see there are 4 equatorial bonds and 1 axial bonds, but all the bond angles are of 90 degrees. The most common coordination number in complexes is 6 and typical geometries for coordination number 6 are octahedral, distorted octahedral and trigonal prism. Here you can see 3 types of geometries. First is planar, other one is trigonal prismatic and third one is octahedral. In octahedral geometry, all bond angles are of 90 degrees, but in distorted octahedral geometry, there will be some distortion in bond angles. Here is an example of octahedral geometry. In octahedral geometry, there are 4 axial bonds with bond angle 90 degree and 2 equatorial bonds. Here also ligand metal ligand bond angle is 90 degree. The hybridization involved in octahedral geometry is D2sp3 or sp3d2. With D2sp3 hybridization, inner orbital octahedral complexes are formed, and with sp3d2 hybridization, outer orbital octahedral complexes are formed. Here is an example of a complex with octahedral stereochemistry. FeCN6 4-. The central metal ion is Fe2+, and you can see that 6 Cn- ligands have made 6 coordination bonds to Fe2+ metal ion. There are 4 equatorial bonds and 2 axial bonds. Now we will discuss coordination number 7. There are 3 main stereochemistries for complexes of this coordination number: pentagonal bipyramidal, capped trigonal prismatic and capped octahedral. The last two being obtained by the addition of a 7th ligand either above one of the rectangular faces of a trigonal prism or above a triangular face of an octahedron respectively. Here you can see the 3 possible geometries for 7 coordination number. First one is pentagonal bipyramidal, which is most common one. Other one is capped triangular prismatic, and the third one is capped octahedral. The higher coordination numbers, that is 8 and 9, are very rare, and these are not required to discuss here. Now you know the important stereochemistries related to the coordination numbers from 2 to 9. You must also know to calculate the coordination number of a metal ion or atom if the formula of the complex is given. This we can understand with the help of some problems. Here is our first problem. What is the coordination number of the cobalt ion in the compound CO NH3 Cl Cl2? To calculate the coordination number, you must only consider the coordination sphere, that is, the part of the complex which is enclosed in the square bracket. You must count the total number of monodentate ligands attached to the central metal ion. Here all the ligands are monodentate. Actually, to calculate the coordination number, the number of ligands must be multiplied with the denticity of the ligand. As in this problem, all the ligands are monodentate, 5 ligands are amine and 1 is monodentate ligand, which is chloride. So, 5 ligands must be multiplied to its denticity, which is equal to 1, and 1 chloride ligand must be multiplied to its denticity, which is again equal to 1. Hence, the coordination number of cobalt in this problem is equal to 5 into 1 plus 1 into 1, which is equal to 6. Here 5 is the number of monodentate ligand amine and 1 is its denticity. 1 is the number of monodentate ligand chlorido and 1 is its denticity. If you have some polydentate ligands in the complex, then we can also calculate the coordination number. To understand that, there is another problem. You can have a look. Determine the coordination number of the central metal atom in Na4, CO, C2O4 whole thrice. Here you can see that oxalato, that is C2O4, is a bidentate or didentate ligand. These ligands are present in 3 number. Hence, the number of ligands, that is 3, has to be multiplied with the denticity of the ligands, which is equal to 2 in this problem. Therefore, the coordination number of cobalt in this problem is 3 into 2 equal to 6. Here 3 is the number of ligands present and 2 is the denticity of the ligand. If there are more than one type of ligands, that is monodentate ligands and polydentate ligands, all are present in one complex, then also you can calculate the coordination number of the central metal atom or ion. To understand that, there is another problem. For the coordination compound K2 CdEn Cn whole 4, what is the coordination number of the central metal ion? In this complex, you can see that there are 2 types of ligands. One Cn, which is a monodentate ligand, and the other ethylene diamine, which is a bidentate or didentate ligand. Again, you have to proceed within the coordination sphere, that is the part of the complex which is enclosed in the square bracket. So, you have to multiply the number of ligands with their denticity and add all the values. There are 4 monodentate ligands and 1 bidentate ligand. Therefore, overall coordination number of cadmium is 2 into 1 plus 4 into 1, which is equal to 6. Here 2 is the denticity of the ligand ethylene diamine and 1 is the number of ethylene diamine. 4 is the number of monodentate ligand Cn and 1 is the denticity of Cn. Now, you are able to calculate the coordination numbers of central metal atom or ions if the formula of the complex is given. In the end, let us revise what we have discussed today. Today, we defined coordination sphere, ionization sphere and coordination number. We also discussed the stereochemistries for various coordination numbers ranging from 2 to 7. In next lecture, we will discuss a very important topic related to coordination compounds, that is IUPAC nomenclature of coordination compounds.